It's video 2 for the energy unit. In the last video, we talked about what work is, and we learned that work is the integral of the force vector dotted with a displacement vector. So, since work is a force over distance, objects held in place have no work done on them. So, if you are holding a very heavy object above the ground, it may take a great deal of effort. However, there's no scientific work being done. So that kind of begs the question, why do we get tired after holding heavy objects? So this kind of really introduces the idea of internal work. You see, you're not doing any work on the object you hold. However, work's being done inside your body by your muscle fibers. In order to hold something in place, your muscle fibers need to contract and expand, continually just to maintain that tension. So we have internal work being done. However, internal work is not considered when calculating the work done on an object. So that explains where this effort comes from. Okay, the next topic is net work. So let's say we have several objects or several forces acting on an object. Each force can do work on the object. So the net work is the sum of all the individual works by the individual forces. So for example, let's take a look at this box. We've got a 500 Newton force pulling on it. And let's say that we have an angle of 20 degrees. So looking at this then, we would also have a friction force. We'll go kinetic friction since this is going to move a displacement. We have a normal force. And we have a gravity force. Looking at the 500 Newton pulling force, notice that it can be resolved into X and Y components. So we can take care of that. Don't forget that friction is the coefficient times the normal force. So we need to do some figuring out to figure out what this normal force is. When studying the forces on the y-axis, we see that we have the normal force plus the y component of the pulling force minus the weight of this object, and we want to be in equilibrium on the y-axis. So those three forces need to equal 0. So looking at this, we see that the normal force then must equal the weight minus the y component of that pulling force. So then, this normal force must equal mg minus F sine of that 20 degrees. We'll come back to that. That's important right there. Okay. Going on with the friction then, we can go ahead and start calculating what the friction is. So we got the coefficient times normal force, but the normal force is at mg minus F sine 20 degrees. And when we plug in our values for that, the 0.1 for the mu, the 2 kilograms for m, 10 newtons per kilogram for g, 500, we find that the kinetic friction is right around 18 newtons. So we can leave that be. All right. So we have 4 forces acting on this object. And the displacement vector, 5 meters, we're going to say is to the right. So notice that forces like the normal force and the weight vector and the y component of the pulling force, those are vertical forces. They're perpendicular to the motion of this object. Well, since they're perpendicular, that means that theta for them will be 90 degrees. And cosine of 90 degrees is 0. So when we take a look at work is the integral of the force vector dotted with the displacement vector. And when we have a constant force, we see that the work then would equal force times displacement times cosine of the angle. So when theta equals 0, cosine of 0 equals 1. When theta is 90, cosine of 90 is 0. So for the normal force, Fy and Fg, those values, the theta is 90 degrees between them and the displacement. So the work they do is 0. However, we see that this x component of the pulling force and the friction force, well, they are not at 90 degrees. So we can calculate the work for them. So first off, we have the work from the applied force. So that one would be F times delta x times cosine theta. So that equals 500 newtons, 5 meters, cosine of 20 degrees. We see that we have a newton times a meter. So that gives us, looks like 24,985 joules. Okay. Then we have work from the friction. So here our force is that kinetic friction force times delta x times cosine of theta. So then this equals, we just found that to be 18 newtons times 5 meters times cosine of 180 degrees. Notice that since the friction is going in the opposite direction of the motion, cosine of 180 is negative 1. So this gives me a value of negative 90 joules. So the net work will simply be the sum of those two. I want to check my math, but that should be pretty close. The next topic is work being done by gravity. So let's say I want to take an object at the ground and I wish to lift it up. By the ground, this object is going to have some initial position, and higher in the sky, it's going to have some final position. So to calculate how much work is needed to lift this object from its initial position to its final position, I can just use my work equation. So the work equals the integral of the force vector dotted with the displacement vector. Now, this force is a constant force. Gravity, when you're near the Earth's surface, gravity is a constant force. As you get farther and farther away from the core of the planet, that's no longer the case. But when we are close to the surface of the Earth, and by close I mean, from the clouds down, we can assume gravity is a constant force. So this work will equal the gravity force times the integral of the displacement vector. Now, also notice that the displacement's up, the force we must apply is up, so those two vectors are parallel, so that gets rid of the dot product for us. So this work vector, we want to evaluate it from the initial y position to the final y position. So the work then will equal, Fg is m times g, and then the integral of dx between those two boundaries would be like that. So if I were to take a look at a graph of my force versus displacement, I would see something like this, and I can then find the area of that to find out how much work is needed to pick up that object. Something else we're assuming here, the force that you're lifting up with is, we're assuming we're lifting this object at a constant velocity. That way we can have the upward force being the same as a gravitational force. So basically, when we're picking this object up, we have an upward force, there's a gravitational force, and what we're saying is the sum of forces on the y-axis needs to be 0. That way, the upward force is the same as the gravitational force pulling down on the object. Now, since we're going against the gravitational field, we are storing energy in the field itself. And gravitational fields are something we've seen before. We can get this stored energy back by simply allowing the object to fall. And notice that this formula for gravitational potential energy will only work, or this formula for calculating how much work, it will only work near the planet's surface. So we're going to need a different formula if we're looking at objects that's even farther, so like for satellites and rockets. Okay, let's take a look at how much work's done by a spring. So in this one, we are stretching a spring. So our force is in this direction. We're going to call it Fs for a friction, or a spring force. Now remember that for springs we have this relationship where the elastic or spring force equals negative k delta x. That's Hooke's law. So when we go to take a look at how much work is needed to pull that spring or compress it, the work equals the integral of the force vector dotted with the displacement vector. This time we no longer have a constant force. The force changes. And it changes because as you pull harder, or as you displace a spring farther from its equilibrium point, the force it has becomes stronger. So we can plug in our formula for that spring force. So it's going to be negative k x dx. Okay, now we got rid of the dot product, and the reason for that is because this elastic force and the displacement vector, they are in the same direction. They're both parallel to each other, so we can get rid of that dot product. There's a negative sign there, and that's because they are in opposite directions. So if I apply a force to the right, or if I pull to the right, the spring force goes against that. So that's why that negative sign's in there. All right, so we can evaluate this integral. I can pull out the constant, so the negative k is a constant. I'm left with the integral of x dx, and I want to evaluate that from some initial position to some final position. In your calculus classes, if you're taking calculus, you'll learn that the integral of x dx is 1/2 x squared. And I want to evaluate that from x not to x. So in other words, the work here, what I'm left with is a negative 1/2 k delta x squared. That's what I'm left with. So if I were to make a graph for this, force versus displacement, what I would find is something that looks like this. And then I'd have to have the area underneath that to get my my work. All right, that concludes video 2.